Thank you, everybody, for being here for my presentation. So the first part of this presentation shows how vibroacoustic method is used as a fast diagnostic tool to easily detect mechanical problems in the tap changers online or offline before they create an outage. The second part will present a real case showing how New Brunswick Power has used this tool to adjust properly an OLTC. So 40% to 50% of failures on transformers come from tap changers and are of mechanical origin. And 4 studies done by Hydro-Quebec, ESCOM, CAA, Canadian Electricity Association, also in Australia, during 10 years on 3 continents, and confirmed by Siguri and IEEE, show exactly the same results. If you see here, like in orange, you can see that Hydro-Quebec has close to 45% failures coming from the tap changers. Here, what are this table shows a brief comparison between the 5 existing methods available today. Vibroacoustic methods offers the widest detection spectrum. This table is from Siguri. For example, you can see that overheating and cocking is marked low for vibroacoustic, but is marked excellent for timing, transition, and arcing. So I recommend that you study carefully this table because it gives you like a global view on what the method exists today. Sorry, I need to. What kind of benefits OLTC's vibroacoustic testing bring to electric utilities? A total of 14 benefits have been identified. First of all, it's applicable to any kind of tap changers, applicable online or offline, quick, easy, and intuitive tests exactly similar to a stethoscope. With vibration and current combined, we are able to detect a large range of potential problems. It gives you a better understanding on how the tap changers works. Thanks to this understanding, we can detect problems at earlier stage. Excellent in terms of timing and mechanical adjustment. That the second presentation will show this in detail. Easy tool to detect arcing contact problems. Of course, it's online only. We have a powerful software analysis thanks to Hydro-Quebec envelopes that simplify the analysis. We have a high sampling time and unlimited recording time unique in the market. It's an excellent tool to help the user to decide which OLTCs are due for a maintenance operation. And in testing OLTCs before and after maintenance, this tool can be used for quality control. And in testing year after year, trending analysis becomes easy and allows a reduction of maintenance interventions. And of course, our goal is to reduce the transformer failures. Here you have a typical resistor OLTC type, and you can see the diverter switch operation sequence. Typically, the transition of the diverter switch is done in only 50 milliseconds to avoid overheating the resistance. And we're able to listen all the impacts of the mechanism during a step-up or step-down operation. And the motor operates between 2 to 12 seconds. In these graphics, you can see here we are moving from tap 3 to tap 4, and with it shows exactly how the resistance are connected during this transition. The motor drive mechanism. So this motor allows the tap changer to move from a position to another. And in recording, analyzing the EC or DC current of this motor during the step up or step down operation, we are able to know if the mechanism are forcing or not. And the motor current allows us also to start and stop the recording. So this way you have an exact window of the event, thanks to the motor current. What is the diagnostic principle? Each operation of any unload produces a specific vibroacoustic wave pattern, or we call this a signature or a fingerprint. With a vibroacoustic sensor, which is an accelerometer, we can record this signal exactly the same way a stethoscope picks up a person's heartbeat. And the fact is simple: a stable OLTC always shows consistent signatures. Any degradation of the OLTC induces changes in the signature. So vibroacoustic measurement, how we do this? The sampling time, what is the sampling time? It's the time interval between two readings, is an important parameter to keep in mind. And for the vibroacoustic, we use 10 microseconds, and I think it's the minimum that we must have. Any value on top of this is not good, which is a sampling frequency of 100 kilohertz. Here you can see the top 4 that we use for this recording. And here you have an example of good and bad recording vibration signals. So if you take a simple vibration of a ball bouncing on a plate, exactly this event has been recorded at 10 microseconds, which is absolutely required for vibration. The same event has been recorded at 100 microseconds. This sampling time is okay for timing, motion, but not for vibration. And here, just to show you what kind of signal we are going to get at 500 microseconds, which is, you can see a totally broken signal. So what, in the next slide, we have done like a zoom of this ball bouncing on a plate at 10 microseconds. You can see a clean and smooth signal. At 100, the signal starts to be broken, and at 500, it's totally broken. So in fact, you record absolutely nothing, just noise. What we need an AC clamp or a DC clamp, 3 accelerometers, but usually we use only 1. Of course, the recording system with the software on the computer, and these are the specifications. As I told you, 10 microseconds. The 16-bit is important. And of course, the computer and the recording system give us the unlimited recording capacity. So here you have an example of connections of Type 4 or Type 4 Plus. Here, so first of all, you have to choose the spot where you are going to install your accelerometer. We use the clue. Here, this is a tap base where the accelerometer is screwed. Here, it's a specific cable, which is which converts in BNC, which is a standard cable. And then here, it's exactly the same for the current. Here, you can see an AC current clamp, or we use also like a DC current clamp. It depends of your tap changer. And the connection between the computer and the recording system is done through USB for the portable Type 4. Here you have the same, exactly the same, but in using what we have an OTMX, which is a standalone event recorder. So it's exactly the same, but this one it acts exactly like a monitoring system. So you can leave it there for months and years connected to your tap changer. So first step, we need to identify the tap changer. So the motor drive mechanism in the control cabinet. And then, so when you know exactly where to install, so here after second step, the accelerometer should be installed at the closest possible location to the transition mechanism. Here you can see the aluminum base on this, the first picture, base which is glued on the second picture at the best location, and then the accelerometer is screwed into that base. This is the third picture on the right. Here you have some examples of accelerometers installation. So here you have some examples of the current clamp installation. Example of test circuits for online test, presence of course of high voltage. we record operation of 1 or 2 taps, step up, and the step down of 1 of 2 taps, and tests are performed in such a way to minimize the impact on the consumers. Of course, as soon as you work on online on your transformer, your consumer will not be happy. For offline test, we record all taps to get a reference. The Hydro-Quebec, so here you can see on the blue, like the raw data, which is the typical Vibro-Acoustic signal given by an accelerometer. And on the blue, on the red one, you can see what we call Hydro-Quebec envelopes, which has been patented in 2001 by Hydro-Quebec. And so here you can see the current. And here we call this high frequency envelope, and here the low frequency envelope. So now why envelopes? Because it simplifies the signal, get the shape of the signal. And so this way we can focus on valuable impacts only. And after, in fact, our target is to have something easy to analyze and something easy to compare with a reference. Here, so every tap changer has a specific sequence of operations that can be identified in the envelopes. And depending on the model of OLTC, different signatures can be obtained, which are characterized by specific operation length, number of peaks, shape of current, amplitude of the impacts, and so on. And the sequence of operations associated with OLTC is described in the operation guide provided by the OLTC manufacturer. Here you can see, like on the blue one, the startup of the motor current. Like in blue, you have the motor current, and here in red you have the high frequency envelope, and here this is the part of the changeover switch, diverter switch, like the first sequence. Here some contactor is acting, the selector switch is silent. Here you have a diverter switch, because like you see typically here it's two transition. And then after you have the braking part, which is important also to analyze. And then after you have the post operation. So this is typically what we do. Here on the left side, you have the raw data. So the motor current, this is an AC. We can see clearly, if we zoom here, you will see like the sine waves. And this is typically vibroacoustic, the impact of the diverter switch. So thanks to this, a diagnosis can be made in 15 minutes for an online test, 1 hour for an offline test. So thanks to the software, we calculate immediately the envelopes, and we get immediately what we call an Excel report. This is the on-site, and here you have I will show you in the next slides how we can do analysis, interpretation of these curves. And after, of course, we have what we call the off-site deep analysis, thanks to the Excel reports, contacts where, the envelope, and we have also a diagnostic card. So that give us a comparison with Zensol database OLTC references signatures. Here you have an example of work of contact before it's how we use the high frequency and low frequency envelope. Before the intervention, more than 60% of difference between the high and low frequencies. So this give us an indication that we have several wear of contacts. And after repair, you can see in the next slide, after the intervention, less than 20% of difference between the high and low frequency. So we have in our report, we have a systematic analysis of these two high frequency and low frequency envelopes, so to be able to have an indication of the status of the contacts if they. Here it's an example of poor lubrication. The unusual part shown on the curve means that the motor is forcing. Usually it's totally flat and flat, sorry. And here, immediately you can see that something is not normal in the motor drive. Example of asynchronism. So this test results show an example of asynchronism of the switching operation. In normal condition, the switching operation should occur before the current stops flowing in the motor. In the case illustrated on the left, the switching operation signal is delayed by 120 milliseconds after the end of the current envelope. As it can be easily observed, this kind of issue doesn't require the use of a reference signature, and the asynchronism can be detected immediately. And the intervention in this case consisted in uncoupling the drive motor and adjusting it so that a switching operation could occur before the motor current drop. And the finger on the right represents the normal condition of the motor of the mechanism after the repair. In this picture, an example of arcing contact is presented. Two tests have been performed on the tap number 10 of the same OLTC. One test has been performed offline, the red curve on the bottom here, and the other one online, the black curve. By comparing the two signatures, a big difference in the maximum amplitudes can be easily observed. In fact, the maximum amplitude of the offline test is Hg, while the other of the online is 35G. So here, this is a zoom of these two, the last impact, the last peak. The image on the right shows the superposition of the two signatures through which is possible to observe the presence of an extra peak in the online test, and this extra peak represents the arcing contact phenomenon. Here, usually we try to do impacts and timing association. So thanks to the information given by the manufacturer that you can see here on the top, and here this is the Vibro-Acoustic signature. So this is the hardest part, in fact, for the analysis of the Vibro-Acoustic is. So it's like to be able to do like a mechanical association with the electrical schematic association. Here you can see an abnormal in-rush current. Here you can see one which is normal and the other one which is flat, which is not normal, and that create like problems with the breakers because it's not normal, so the breaker operates, and so this is just a bad adjustment of a timer inside the control cabinet. It was this test has been done on a totally new transformer with a tap changer. Here it's exactly the same forcing current and abnormal. So it's easy to see because it has to be flat. So this is the kind of problems that we can detect very quickly. Here you have, here is an example of motor drive current analysis throughout the years, and we can notice some malfunctions after the in-rush current on the braking part. Here it's like two problems of bad connections. So here other example of inconsistent setup connections. So throughout the years, like one measurement has been on 2014 that you can see on the top here, and 2016 in the middle, and 2023 the last two ones. So you can see that the motor current, the connection was not consistent. Example. So the analysis of the braking mechanism is an important part of evaluating the health of an OLTC. This is done by observing the appropriate portion of the recorded current and the corresponding vibration measurement measured by the accelerometers, and other relevant information should be sourced from the manufacturer manual. So they like to do a quick story. What you have to analyze is the inrush current, the flat portion of the for the operation, and at the last it's the breaking part of the current, and of course how you have to analyze at the same time the impacts that you impact recording. So now the challenge is how to facilitate the compression of a vibroacoustic signature. Several mechanisms are operating at the same time. So one way to address this challenge is to analyze simultaneously three recordings: the vibration, the dynamic resistance, and the motor current of the tap changer in action. So what we need what we call a tap 4+ with an accessory that whose name is tap DRM, and of course the tap changer is the transformer is offline totally, and in fact the tap DRM is a current source. So this is an example, a typical example of a DRM recording. I hope that you are familiar with this curve, which shows exactly how the transition is done during a diverter switch operation. And here you can see the contacts while they move. You can see the correlation between the electric schematic on the bottom here and the mechanical movement. So I'm going to show you you see, so here you get the impact. And now we have moved from 1 to tap 2. So I can just show you quickly. So this is where in tap 1. Then we move. Now we are in tap 2. So dynamic resistance here, this electrical association. So step 1, step 2, step 3, step 4. So, and then we have, so this is the kind of, we have the dynamic resistance of the first curve, the vibration, and the motor current. Like, but if you have only the vibration and the motor current, so it's hard for you to understand why we have 4 impacts, you see. So with this, when you do this correlation, it helps us, in fact, to learn the vibroacoustic signal and to understand it. So it's exactly the same. So here you can see the DRM and the vibroacoustic and each part. So the correlation is easily done because you cannot do any wrong interpretation with the correlation of these 2 signals. So this is some examples of recording for different OLTC done by tap 4+ and the accessory tap DRM. Here, this is other examples. This is the global setup, tap DRM, the accessory, the tap 4+, the current EC clamp. So here, in general, it's good to put like a tag. So this way, the next year or in 2 years, you will come back exactly at the same location to avoid any wrong connections, because it's important when you compare 2 signals to compare them exactly at the same spot. The accelerometer and connected to a transformer connection. So here is an example of a typical recording. Looking at image on the left, the total operation time shows 6 seconds on the bottom left. Looking at image on the right, the resistant transition and the corresponding current drop are highlighted. You can see here current drop, current, voltage, resistance, and vibroacoustic. And we can also see the vibroacoustic signal of the diverter shown by the accelerometer curves. Shown are several step-up and step-down operations recorded in a single test. Look at the arrows showing that voltage or current are not interrupted, and such tests are performed for tap positions where we suspect that there might be a problem. So we go up and down this tap position to gather data to troubleshoot the problem. And here we see an example of a DRM analysis, and in the next slide, we zoom the resistance. So after we know exactly which when the impact has occurred. Example of action plan to elaborate predictive maintenance for transformers with OLTC. Step 1, establish your transformers list with OLTC to monitor. Step 2, for each transformer, do a complete test to get a reference. All taps offline, tap 4+ and tap DRM. We have developed Zensol checklist. Step 3, produce a complete report analysis for each OLTC transformer, and we have developed a Zensol template report analysis, and I can guarantee that at the end of this report, you will understand absolutely how your tap changer is working. Step 4, according to diagnostic results, you can establish your maintenance plan for each transformer, and after you just have to go through a periodic vibroacoustic test online or offline. So this is, I come now to my second part of the presentation. Of course, this presentation has been developed by Christian Noël, who is a professional engineer at New Brunswick Power, and he has presented this the first time in January 10th, 2023. So this test has been done in Caracat, LTC maintenance with a MR type M3, Vibroacoustic, and DRM performed before and after maintenance. And this maintenance was performed on our Caracat T1 transformer. And this transformer is equipped with a Renhausen type M3 Delta 500 tap changer. So in general, there are two types of LTC, compartment of box type and in-tank design. In our case, this LTC is an in-tank design. Although most of our in-tank design LTCs are 3 separate phase models, we do have a few delta configuration, and the delta configuration has a cylinder with 2 diverters, and the other is a regular cylinder with a single diverter that you can see on the right picture. And timing between the motor drives and diverter assemblies is adjusted using the shaft connections between them. In this case, we installed 2 vibroacoustic sensors, 2 on separate walls near the diverters and located about 8 inches from the cover. In fact, they have used 2 just to be sure that they got exactly the same result. But as I told you in the beginning of the presentation, we need only 1. And here, this is confirmed exactly what I told you. Here you have the 2 accelerometers. So in fact, the analysis is done with the 1 is enough. Generally, tap operation, this type of tap changer will include the following steps. One of the selector contact is leaving the previous tap position stationary contact. This moving selector contact is then connecting to the next tap stationary contact. The energy in the diverter energy accumulator is released to switch the load current to the next tap connections. On this graph, we are seeing the sound made by each operations being captured by both vibroacoustic sensors and also the motor current captured by the EC clamp on the CT. when adding the DRM information to the previous graph, we can then confirm that when exactly the diverter are switching the current. It helps understand the information provided by vibroacoustic sensors. Here, it's what you see here. In fact, you have the current and the voltage, because to be able to calculate the resistance, you need two analog channels, one for the voltage and one for the current. And of course, we use Ohm's law. So the results shown are from before the maintenance. We are seeing all three phases side by side. From this information, we can tell that A phase is not operating in sync with B and C phase. E phase is likely the single diverter when B, C phases are associated with double diverter cylinder. So I hope that you can see clearly that the phase A is not in synchronization with the B and C. Clearly, you see, just thanks to the impact. And now, if you don't have the DRM information, you will have here two impacts, and you will not understand why you have these two impacts. So when you add the information of the DRM resistance, so at this time you can do your correlation, and you understand that the acoustic impact is coming from this one on the left, the first one. Our test plan calls for testing all the tap transition going up and also back down. In this up operation, we're seeing that A phase is operating earlier than BAC. I hope that it's clear here. But in the down operation, we are not only seeing that A phase is operating slightly later than the other two phases. In fact, A phase is operating after the motor current is interrupted. The timing of this diverter is at the limit where it could possibly not operating during a down operation, and this would result in a phase being on a different tap than the other two phases. This graph is now showing the acoustic signatures and DRM information recorded after our maintenance. We're seeing A phase operating now around the same time as B and C phase, about 4 and 25 seconds. But the big improvement can be seen on the down operation, where A phase is operating well within the runtime of the motor now. This aligns with what was seen for B and C phase. So just to review the before maintenance reading showing the difference in timing between A phase and the other two phases. So it was the first, the before maintenance. And now the after maintenance results now indicate the timing between all three phases is now better adjusted, and the selectors and diverter operations are now more in synchronization. I'm not showing the down operation, but the timing was the same as the up operation shown on this slide. So now they are perfectly adjusted. So it's why Vibroacoustic is really, in the beginning, what kind of benefits the Vibroacoustic brings to utilities. The timing and the mechanical adjustment were highlighted. So Zensol Tap 4 can give a good indication of the timing between diverters. When time allows, it can be used before and after maintenance to validate the LTC is operating properly after our intervention. As we're gaining more experience within the information provided by the Tap 4, we could use offline acoustic measurements to focus prioritized maintenance on specific units. So in fact, the idea around this is to do, if you have, for example, a limited time for the maintenance in summer, what we do, you do a quick vibroacoustic test on all your transformer with tap changers, like if you have, for example, 10, and then after you choose on these 10 transformers, which one you are going to go deeply. It's what we call to focus and prioritize the maintenance on specific units. So thanks to this quick tool, you can decide which transformer would receive like a deep maintenance. So, Randy, I think it's okay for me.
Well, that's great. Good presentation. Let's yes. Let's see here. What are the challenges and limitations of implementing vibroacoustic diagnostics? What are the challenges of doing it? We know the benefits, right? But what are the challenges and limitations of doing that?
Well, if you use the Vibroacoustic, in fact, for me, it's simple.
Mm-hmm.
It's not the challenge is in the interpretation of the vibroacoustic signal, because you get impacts, you get some recording, and after you need to understand what is this impact, and the challenge is well easy to do, very easy to do the test, very easy to but as soon as you get your curves, your signals, your start work, your work starts. Sorry.
Mm-hmm. Right.
But
Well,
for me, it's not a challenge. The challenge is it's the after the recording.
right. Okay. And the if I understand it correct, the benefits is that it's non-invasive, so it's like non-destructive testing,
Absolutely.
and it's early fault detection.
Yes, because look, when you are able, we are able. The tap changer is a mechanical part, right? So if it's a mechanical part, the sound produced by this mechanics will give you an indication of the good adjustment or bad adjustment of this complex mechanism.
Mm-hmm. And you said at the beginning of the presentation that maybe half of all transformer failures are because of onload tap changer failures, correct?
Yes, exactly, and they are of mechanical origin. So just imagine that 50% of all your faults come from the tap changer.
Mm-hmm.
And are mechanical because it's a complex part.
Yeah, because a lot of transformer maintenance is refers to the oil, correct? Oil
Yeah.
testing and all of that. But people don't realize that half of the faults are mechanical faults.
Yes, exactly.
Okay.
And very, very strangely, that we can see exactly the same for the high voltage breakers,
Okay.
like the
Here's
failures here.
here's another question. Have you ever experienced any case of noise signal coming from your vibration sensor?
What do you mean? The
Car, Car,
accelerometer?
Carlos Reyes asked that question. Have you experienced any cases with noise signal coming from your vibration sensor?
No, because an accelerometer is record the vibration of your transformer. It's not an acoustic. We call vibro-acoustic, but it's not a microphone.
Okay.
An accelerometer is not a microphone. In the past, like Hydro-Quebec, they have started, and also TEPCO in Japan, I think it was in 95, they have tried their research in using the microphones. And during 2 years, but after 2 years, they have noticed that in fact it's hard because the high voltage transformer is noisy, right? You have you have a lot of noise, and the substation also is very noisy. So in fact, after 2 years, they said no, it's really hard to differentiate between the noise coming from the fan, or you see, or so it's why after they have stopped this TEPCO, they have stopped their research, but Hydro-Quebec, they have continued, but they say, okay, no, we are not going to use microphone, we are going to use an accelerometer, and we are going to put our focus on the vibration of the transformer. And what is good for us is that the tap changer has a noise on top of this global noise. Do you understand what I mean? Because
Yep.
it's an impact. It's an impact that you listen, that you're able to listen, even in a noisy environment, because we get a vibration of a metallic part of the transformer.
Okay.
I hope I have been clear.
Oh yeah, crystal. Okay.
Thank you.
Okay. Thanks very much. That was a good presentation as always. Thank you.